Now we want to look at line integrals of vector fields. Now we just looked at line integrals where the integrand was a function of x and y. Now we want to look at line integrals where the integrand is a vector field. Now, line integrals of vector fields have two important considerations. First is that the answer depends on the orientation of the curve in relation to the vector field, and we're specifically talking about the component that is tangential to the curve. From the definition of vector line integrals, you can see that we're adding up the tangent components in the vector field. So we'll use the bold capital T as usual to represent the unit tangent vector at each point in C, and since it's pointing in the direction that C is being constructed, we'll use that as our positive direction. So we know that the component of F in the direction of the unit tangent vector is given by the magnitude of F times the cosine of the angle between them. Now, since the unit tangent vector has a magnitude of 1, we can multiply by the magnitude of 1, which is t, and get magnitude of F times the magnitude of t times the cosine of theta. Well, that happens to be the definition of the dot product of F and t. And so our integral, our line integral of the vector field F over the curve C is given by the dot product of F and t summed up over the curve with respect to arc length. Now, just like with scalar line integrals, it is not easy to use the line integral in this form because we would then have to parameterize every curve by arc length, which is a little cumbersome sometimes. So we'll do some rewriting. Typically, the curve that we're integrating over is given in vector form. I'm using an example that's three-dimensional, x, y, and z being the components of the vector r. However, the unit vector t is described as the derivative of r divided by the magnitude. So we're going to change our integral by replacing t with what's equal to t, and we did this with the scalar line integrals. We're going to replace the ds with the magnitude of r prime t dt. And so we get this integral, which simplifies to this. Now, this is probably the most useful version of the line integral of a vector field. However, another version of the line integral of a vector field that we oftentimes encounter is this. Now, we're going to use the vector f, g, h to represent our vector field. So the first and second and third components. And again, if we only had two components, then it would be f and g instead of f, g, and h. And the derivative of r, we're using x prime, y prime, and z prime. And so we can write f dot r prime in its expanded form and simply recognize that we can replace the x prime t dt with the differential dx. And we can replace the y prime t dt with the differential dy, z prime t dt with the differential dz. And so we get the version of the line integral of a vector field, which we call the differential version, that looks like this. And finally, if we use the r prime t dt as the differential of r, we can rewrite our line integral as simply f dot dr. So this is usually what you see when we talk about vector line integrals, just a f dot dr, but that is not the working version of the line integral of a vector field. Now here's a page that kind of summarizes all of the things that we just went through, and like I was saying in the beginning, typically what we see when we talk about line integrals of a vector field is just f dot dr. Probably the most used version is this. However, we do occasionally see differential version. So let's work through some examples. Here we've got the vector field given, we're talking two dimensions, y minus x comma x, and the curve that we're integrating over is described as the piece of the circle going from the point 0, 1 to the point 1, 0. So here is a maple graph of the vector field. Here is the curve drawn over the vector field. Now, before we get to the actual calculation, let me just point out that if you have a look at the curve and the vector field, you'll notice that up in this region, our vector field is pointing in this direction, our curve is pointing in this direction. So do you notice the curve and the vector field are kind of working together in that area? However, down here we notice the vector field is pointing in one direction, the curve is going in the opposite direction. So we've got the vector field and the curve working against each other. So what does our line integral of a vector field do? It adds up all of these. If we have more of the curve working along with the vector field than we do the curve working against the vector field, then we will get a positive value for the line integral. If, on the other hand, the two are working against each other, we will get a negative value for the line integral. So the first order of business would be to parameterize the curve. Now, this one's not so hard since we are talking about a circle. Remember, however, we have to get the direction right. So we'll use the parameterization r equals sine t cosine t. That's the one that goes clockwise. If you reverse those, cosine t, sine t, you'd be going counterclockwise. And as you can see from our picture, we're going from 0 to pi over 2. And we do the derivative. We take the vector field and replace the x with sine t, the y with cosine t from our parameterization, and do the dot product. We'll simplify that some, maybe use some identities on it. And then we want to integrate that. And so, does that sound plausible? I'm looking at the picture, and I do indeed see more of the curve that is going against the vector field than I see going along with the vector field. Now we're going to take the same vector field, only we're going to reverse the direction on the curve and go from 1, 0 to 0, 1 along that circle. And we have to reparameterize the curve. Now, I've already mentioned that would be cosine t sine t this time. We'll do the derivative, convert our field into t's. Again, this comes from our parameterization. Then we do the dot product, simplify some, and integrate that. Here's an interesting thing. Does it make sense that we get the same value, only opposite sign? We're going the other direction. And so again, there's as much curve in the direction of the vector field this time as there was in the opposing direction before. And so we just changed signs. So now, what if we take the same vector field and go between the same 2 points, only instead of going along a curved path, what if we go along the straight path? Just like before, we need to come up with the parameterization for that line segment from 1, 0 to 0, 1. We've done this in the past, so here's the proper parameterization for the curve. We do its derivative. We convert our vector field into t's using our parameterization. We do the dot product and then integrate that. Well, this integral comes out to be the same thing we got whenever we went along the curved path. Now, I don't know if you can visualize or even try to visualize what is being talked about here. In particular, I need you to think about, is this something that is universally true, or is there something in this particular situation that causes this to be true, that we can go from the point 1, 0 to 0, 1 along 2 different paths and get the same value. Now, before we evaluate this line integral in differential form, let me just point out that it doesn't really look like a vector line integral. However, if you go back a few minutes in the video, you'll see we talked about this. The component of the dx is the x component of the vector field. The thing beside the dy is the y component of the vector field. So within that line integral, I can recognize here is the vector field. That doesn't really have anything to do with how we're about to compute the line integral. These are actually easier to compute because we don't really have as hard a time with our parameterization. We can simply take the description of the line segment, write that simply as a function. For example, this line could be written as y equals 2x plus 2, the line with a slope of 2 and a y-intercept of 2. Only remember, it's going from x equals 0 to x equals 1. And if we just take that and use it to compute dy, we can then take our line integral, replace all of the y's with 2x plus 2 and all the dy's, the only dy, with a 2 dx. Now again, since we have all dx's now, we know that the limits on the integral would be from 0 to 1. Now, we could also write the equation of that line as x equals 1/2 y minus 1 and do the same thing that we just did. Find dx, replace all the x's with 1/2 y minus 1, replace the dx with 1/2 dy, and evaluate it that way. So either of those two integrals would give us the result we're looking for. Or we could parameterize the curve in terms of t's. And so this would be the usual parameterization for the line segment from 0,2 to 1,4. And we substitute all of the x's with a t, all of the y's with a 2 plus t, 2t. We'll replace dx with dt and dy with 2dt. And then evaluate those. Now, if we reverse the directions on this and go from 1,4 to 0,2, we'll need to reparameterize if we're doing it in terms of t. And you notice that we get the opposite value, which of course we kind of thought we should, since it's the same type of thing we were just talking about, vector fields. Now this is just an observation, which again, it's not evident because in differential form, we don't always recognize that we're talking about the vector field. Now we want to investigate a couple of situations that arise when we're talking about closed curves. Here I've got the vector field in green and a closed curve, ellipse, in blue. For purposes of discussion, we're going to locate a point on the ellipse, and I've highlighted a vector that is at that point in the direction of the vector field. Now, it doesn't really mean that there's any greater effect at that point. I've just made it bigger for us to be able to see what's happening. And so we want to look at a calculation known as the circulation, which basically is exactly what we have been doing, only now we're going to use the word circulation. Well, circulation implies we want to know how much of the vector field actually works around the curve. So we want to add up all the tangential components, which is again is what we just been doing. That is the vector line integral that we've just computed. Now there's another vector line integral that we call flux. Flux measures the amount of the vector field tending to flow out of the region. And so we want to measure the normal component of the vector field. So we want to know at every point along that ellipse, what effect does the normal components have? And so we will do F dot N, and that is called our flux integral. Now to actually compute the integral, what we're going to do is use the outward direction, and again we'll be calling this positive flux. So positive means outward. So here's our little explanation for why the formula works the way that it does. If we take the normal vector, which is the derivative of the unit tangent vector, do the cross product with that and the vector 0, 0, 1, which gives us positive outward, upward, I guess it would be if you thought of it in 3 dimensions. Then look at what we come up with. We come up with the vector, unit tangent vector with respect to the derivative of the unit tangent vector with respect to y, comma, negative derivative of unit tangent vector with respect to x. So if this is our unit tangent vector, this would be our unit normal vector. And so if we substitute that into f dot n and replace the ds with what we've been replacing it with, this would simplify to f dot, and then the vector that we would dot it with for our flux integral would be y prime comma negative x prime. Now we can tweak the definition, the formula, just a little bit by using the symbolism for the vector field f comma g and doing the actual dot product and replacing x prime dt with dx, we get this. Now notice the similarity between this and the previous one, and also the differences. I'll highlight those now. Now again, the circulation integral is what we have been doing. And notice you've got f dx, g dy. Everything's kind of nice and ordered. But on the flux integral, the f and g are still in the same order, but we've swapped the dy and the dx and changed the sign. So here's a typical example of a computation of the circulation and flux on this curve by this force field. Here is the picture, and you recognize that because it's the example I've been using. Now before we actually compute these, let's just have a look. I notice that if I'm looking at the force field in this area, I see the force field that's acting like this along the curve. Well, over here, I see the force field acting like this along the curve. So I'm thinking that it's kind of symmetric. The force field is symmetric, the curve is symmetric, so I'm thinking whichever direction this curve is, I'm thinking there's just as much force from the field acting with the curve as there is acting against the curve. Let's see if that works out. So here is our circulation integral, and again, that's not what we actually compute. We'll parameterize our curve. We'll do the derivative of that. We'll change f using our parameterization into t's. We'll do the dot product, and then we'll integrate that. Seems to match what I thought in the beginning. Now before we calculate the flux, let's take a look at our graph here. Notice, remember, flux is the outward flow across the curve. And I see right in here, see, we've got the field doing this, and we're measuring the portion that's normal. So again, we're wanting to project this vector onto this vector. So this is about half of the other vector, maybe a little more. But in here, our vector is like here, and our normal is here. They're pretty darn close to each other. And so the normal vector is working pretty much in the same direction as the field. But I see all the way out here, everything looks like it's coming out. And I'm expecting then quite a positive answer. Let's see about the calculation. So if we use this version, we'll parameterize or change our field into t's from our parameterization. We'll do the dx and the dy from up here and substitute those into the definition. Now again, we're going all the way around the curve and then evaluate that integral. Sure enough, it does come out to be quite a positive value.